Okay, just to recap then, what we did in the previous video was we worked out this matrix Q, which was the inverse square root of the correlation matrix for X, the covariance matrix for X, times the covariance matrix between X and Y, times the inverse square root of the covariance matrix for Y, and we took it singular value decomposition. So if the sigma i's are the ordered singular values, ui the left singular vectors, vi the right singular vectors, then we found that we maximize the covariance between A transposed X and B transposed Y by taking A equal to SXX inverse square root times U1 and B equal to SYY inverse square root V1. And I'm going to call that A1 and B1 to indicate these are the first CC vectors. So what we're going to do now is think about the second pair and the third pair and so on of CC vectors, of canonical correlation vectors. So just like we did with PCA, we're again going to think about maximizing with respect to A and B, A transposed S, X, Y, B. And we're still going to want our constraints so that A transposed S, X, X, A equals B transposed S, Y, Y, B equals 1. But now we're also going to want some correlation constraint as well. So we're going to want, I'll tell you the constraint first, and we'll see why it's a sensible constraint. We're going to insist that A1 transpose SXXA equals B1 transposed SYYB equals 0. Okay, so it's the same problem as we had before, but we've got the additional constraint that the next pair of variables has to be not quite orthogonal, but it's like the orthogonality constraint we had in PCA, but we've inserted this covariance matrix in the middle. So let's think about why that is useful. So our first transform variable, eta1, was A transposed X, A1 transposed X. And our next variable, let's call it eta2, is also going to be of the form A transposed X. But let's choose A so that the covariance, the correlation between eta1 and eta2 is 0. Yeah, if we're going to transform the variables, it makes sense to transform them to be uncorrelated. Otherwise, they're measuring the same information twice. So if we think about the covariance between eta1 and eta2, well, that's the covariance between A1 transposed X and A transposed X. And you'll be able to see this is just A1 transposed the covariance between X and X times A, which is just SXX, so this is A1 transposed the covariance matrix between X and X and A. So that's where our constraint comes from. If we set this equal to 0, the covariance between eta1 and eta2 to be 0, it's the same thing as setting A1 transposed SXXA equals 1. Okay, and that was the constraint we chose up here. And the same thing will work out for the B's. Okay, so this is the optimization problem we're going to want to solve. Maximize this covariance subject to the length being 1, the vectors, this transform length, and that the correlations with the previous canonical correlation variables is 0. So the question is, what's the solution going to be? And if you've been paying attention in the PCA video, and this looks a lot like the PCA material, it probably isn't going to surprise you to find that the solution is to take a to be sxx negative square root. And instead of, so that's going to be a2, instead of it being u1, like we had before, it's going to be u2 here. And similarly, we're going to take b2, the second canonical correspondence variable, to be syy negative square root of v2. And then we're going to find that a2 sxy, so a2 transpose sxy b2 is going to be the second singular value. Okay. So let's write this out in full generality. So our problem is going to be for k equals 1, 2, up to the rank of sxy. We can't go beyond that. We're going to want to maximize A transposed S xy b. So let's write down the interpretation of what that is. That's the covariance or the correlation between A transposed x and B transposed y. So maximize this subject to, well, we've got two constraints here. A transposed S x x A equals 1 and B transposed S y y B equals 1. And these, if we think about what they are in real terms, this is just saying that that 1's got to equal the variance of A transposed x, and that the variance of B transposed y has to be 1. Okay, so that's phrasing it in terms of our original problem, original variables. Then we've got the additional constraints that AI transposed S x x A got to equal 0 and BI transposed S y y B got to equal 0 for I equals 1 up to k minus 1. And these are the constraints that the covariance between AI transposed x and A transposed x has to be 0, and that the covariance between BI transposed y and B transposed y has to be 0. Now I just wanted to note here that another way of writing down this problem, so instead of writing it as a problem for k equals 1, 2, etc., we can write it down just all in one go like we did for PCA. So this problem could similarly be written as this is maximize the trace of A transposed S x y B. So if you think about what this term is going to be, it's going to be the sum of the AI transposed S x y B I equals 1 up to k, say. Subject to, we want A transposed S x A equal to the identity, and we want B transposed S y y B equal to the identity. So this is written down the problem in the same way we wrote PCA and the way we wrote it at the introduction to this part of the module, as maximizing some functional data subject to some constraint on some matrices. Where here in this case we've got our matrices A is going to be our column vectors A1 up to AK, and similarly B is going to have columns B1 up to BK. And the solution we're going to find is that we must take AK to be SXX minus a half UK, and BK to be SYY minus a half of VK, where Q is SXX minus a half sxy syy minus a half, which is in its singular value decomposition we're going to write as sigma I ui vi transposed. Okay, so the solution is to take the left singular vectors, the right singular vectors, scale them by the inverse square root of the relative covariance matrices, and when we do this, the value of the objective is that AK transposed S X Y BK is just sigma K. Or in matrix notation, we get that A is S X X minus a half times U, and B is S Y Y minus a half times B. Okay, where U and B are the columns, the matrices of left and right singular vectors. So U sigma B transposed. So the proof of this we're going to work through in the example sheets. Okay, but it relies upon the following proposition, which is the analog of what we had before, is that if for any matrix Q with SVD, singular value decomposition Q, equal to the sum of sigma I U I V I transposed, the solution to the optimization problem maximize A transposed Q B, subject to the A's being length 1, the B's being length 1, and the AI's being mutually orthogonal, BI's being mutually orthogonal. Okay. The solution to this is to take the AI's to be the left singular vectors and the BI's to be the right singular vectors. Okay. And the proof to this is very similar to the proof of the proposition we had in the last video, so I'm not going to go through that. I'm going to let you go through it yourself. And we'll talk about the examples class. So just to summarize then, the kth canonical correlation is sigma k. This is the kth largest singular value of Q. We've got the kth singular canonical correlation vectors, sometimes called the weights, are AK, which is S X X minus a half UK, and BK, which is S Y Y minus a half VK. And we've got the kth canonical correlation variables, which are eta k, which is AK transposed X minus X bar, and psi k, which is BK transposed Y minus Y bar.